Thank you. Hi. So I'm Sasha, a postdoc with the Neerwolpert Gyamen and Mate Engelen Computational and Biological Learning Lab in Cambridge, and today I'm trying to tell you about our work on continual learning, continual motor learning with closed loop interactions. Surprisingly, humans, even when introduced with a very, very simple setup that includes just a reaching task and some perturbations, exhibit a very diverse repertoire of non-trivial learning patterns. And these include, but are not limited to, savings, which means that relearning is typically faster than learning. Effects of perturbation, abruptness on the subsequent retention and washout, recovery, which means that when something was previously learned and then there was a washout, then probably there will be some recovery of the previous adaptation, and many other phenomena around the same ballpark. As for models that cover broad repertoire of phenomenology, I will tell with some care that there are no many of them on the market. So there is a model there is a Bayesian normative model from our lab, work by James Hill et al. But as for some more mechanistically plausible thing, we are not very aware of such models. Again, the literature is very broad, and there are some models that focus on very, very specific aspects, such as contributions from Professor Kaigo Gaich group that we heard of yesterday. But focusing on the broad repertoire, there is no much offer. So our model is ridiculously simple. In the core is just a multi-layer perceptron that learns to predict the force that subject has to exert at the next step based on what they experience at the current trial. Then we present the subject with present the model with this force in the following way. We assume that it sums up from the output force that subject outputs and an error. So these two signals sum up and go through the closed loop to the core network. And on non-channel trials, it's just trivial, just basically the same story as what I said before. And on channel trials, where error is zero, there is no learning, no error feedback, and the system is just some closed loop, one-dimensional system that might converge to some non-trivial fixed point. Again, at adaptation trial, if we consider the input-output mapping of the core network, it will just learn to adapt to identity gradually, and then when you release it to autonomous trials, it will converge to some fixed point. And this accounts for both of the phenomena that we discussed. And importantly, linear models can't cope with it. They can't explain any retention of behavior after complete washout. As a result, we were able to fit our model to different data. One thing that's worth mentioning, for saving data from recent paper by Avram et al., we were able to slightly extend it beyond what people usually do, and not only train it, but also to have kind of test set on which we test our model. This is not seen. The points that are covered by dashed line is something that the model wasn't exposed to, the fitter wasn't exposed to during the fitting process. And you can see that in this highlight plots, it's very predictive of what the subject will actually do when they are introduced to these saving trials. So to conclude, the combination of continual learning and closed-loop dynamic can explain much of motor learning phenomena. And the framework is ridiculously simple. It's wide MLP, which is tractable by constant NTK methods, and then a very low D feedback, which is also pretty tractable. And please come to the poster if you want to discuss it in more details.